The sun is getting brighter, not in some poetic metaphorical sense, not in a way that requires a telescope or a satellite to detect. The sun is physically, measurably, irrevocably getting brighter. It has been getting brighter every single day since it formed 4.5 billion years ago, and it will continue getting brighter every single day until it dies. Right now, at this moment, the sun is about 30% more luminous than it was when the Earth was born. 30% more energy pouring out of that nuclear furnace every second, flooding the solar system with heat and light that has been steadily, relentlessly increasing for longer than life has existed on this planet. And here is the part that most people never hear. This increase is not going to stop. It is not going to slow down. It is not going to plateau. The sun will continue to brighten year after year, century after century, millennium after millennium, until the consequences for the Earth become catastrophic, not in some vague, distant, abstract future. On a timeline that science can calculate, on a timeline that has specific dates, specific thresholds, specific moments when things that are alive right now on this planet will no longer be possible. Tonight, we are going to walk through that timeline year by year, step by step. From right now, from this quiet moment, all the way forward through hundreds of millions of years, through billions of years, to the moment when the sun swells to a size so enormous that it fills the Earth's sky from horizon to horizon, when the oceans have been gone for eons, when the atmosphere has been stripped away, when the surface is nothing but molten rock glowing under a red sky, and finally, to the moment when the Earth itself may cease to exist as a recognizable world. This is not speculation. This is confirmed astrophysics. The physics of stellar evolution is one of the most well understood areas in all of science. We know how stars work, we know how they age, we know how they die, and we know with uncomfortable precision what our star is going to do to our planet. So let's begin. Let's start with the sun as it is right now today. And then let's walk forward slowly into the future that is already written in the physics of hydrogen and helium and gravity. The sun is a main sequence star. That means it is in the long, stable middle phase of its life, fusing hydrogen into helium in its core, producing the energy that lights and heats the solar system. It has been doing this for about 4.6 billion years, and it will continue doing it for about another 5 billion years. The main sequence phase is the longest phase of a star's life, and we are roughly in the middle of it. The sun is, in a very real sense, middle-aged, but middle-aged does not mean unchanging. The sun's core is a nuclear furnace, where hydrogen atoms are smashed together under temperatures of about 15 million degrees Celsius and pressures so extreme that the hydrogen nuclei overcome their electromagnetic repulsion and fuse into helium. This process releases energy, the energy that becomes the sunlight warming your skin, the daylight filling your room, the photosynthetic power driving almost all life on Earth. Here is the mechanism that drives the sun's brightening, and it is worth understanding because it explains everything that follows. As the sun fuses hydrogen into helium, the helium accumulates in the core. Helium is denser than hydrogen. It takes up less space. So the core gradually contracts under its own gravity, becoming denser and hotter. A hotter, denser core fuses hydrogen faster. Faster fusion means more energy output. More energy output means a brighter sun. This is a one-way process. The helium cannot be turned back into hydrogen. The core cannot be cooled down. The contraction cannot be reversed. Every second that passes, the Sun converts about 600 million tons of hydrogen into helium in its core, and a tiny fraction of that mass, about 4 million tons per second, is converted directly into energy via Einstein's famous equation, E equals mc squared. That energy works its way outward through the Sun's interior over thousands of years, and eventually radiates into space as light and heat. And as the helium builds up and the core contracts and heats, the rate of fusion increases and the Sun gets brighter. The rate of increase is slow by human standards, about 1% brighter every 100 million years. That sounds negligible. 1% over 100 million years. Who would notice? But the Earth's climate system is extraordinarily sensitive to changes in solar energy. Small changes in the amount of energy reaching the Earth can have enormous consequences over geological timescales, and 1% per 100 million years sustained over billions of years adds up to a transformation so complete that the Earth of the distant future will be unrecognizable. Let's walk through this timeline, starting from now, right now, the present day. The Sun's luminosity is about 3.83 times 10 to the 26 watts. The Earth receives about 1,361 watts per square meter of solar energy at the top of its atmosphere. The global average surface temperature is about 15 degrees Celsius. The oceans cover about 71% of the surface. The atmosphere is 78% nitrogen, 21% oxygen, and about 0.04% carbon dioxide, with variable amounts of water vapor. Life thrives in virtually every environment on the planet, from the deepest ocean trenches to the highest mountain peaks, from boiling hot springs to frozen Antarctic ice. The biosphere is rich, diverse, and resilient, the product of nearly 4 billion years of evolution, but the clock is ticking. Not the clock of human civilization, not the clock of climate change driven by greenhouse gas emissions. Those are real and urgent problems, but they operate on timescales of decades to centuries. The clock we're talking about tonight operates on timescales of hundreds of millions to billions of years. It is the clock of stellar evolution, and it cannot be stopped. Let's move forward. 100 million years from now, the Sun is about 1% brighter than today. 1% doesn't sound like much, but the Earth's climate system amplifies small changes in solar forcing through feedback mechanisms. More solar energy means slightly warmer oceans. Warmer oceans release more water vapor into the atmosphere. Water vapor is a greenhouse gas. More water vapor means more heat trapped, which means more warming, which means more evaporation, which means more water vapor. This is a positive feedback loop, and it means that a 1% increase in solar luminosity produces more than a 1% increase in surface temperature. At this point, 100 million years from now, the effects are subtle. Global temperatures might be a degree or two higher than today, all else being equal, but all else is not equal. The Earth's climate is also affected by the configuration of the continents, the chemistry of the atmosphere, the biology of the biosphere, volcanic activity, and many other factors. Over 100 million years, the continents will have drifted significantly. The Atlantic Ocean might be wider. New mountain ranges might have formed. The geography of the planet will be different, and that geography will affect climate in ways that are difficult to predict precisely, but the solar forcing is relentless. Regardless of continental positions, regardless of volcanic activity, regardless of biological evolution, The sun is getting brighter, and that extra energy has to go somewhere. Let's take a breath here. Feel the quiet of the room around you. We are still in relatively familiar territory. 100 million years is a long time, longer than the entire age of the dinosaurs' reign. The Earth will change enormously in that time, in ways both geological and biological, but it will still be recognizably Earth. Oceans, continents, an atmosphere, life. Possibly very different life from what exists today, but life nonetheless. The 1% increase in solar luminosity is a background hum, barely noticeable against the louder symphony of plate tectonics and evolution. But it's there, and it's growing, 200 million years from now. The sun is about 2% brighter. The Earth has been through significant geological changes. If current plate tectonic trends continue, a new supercontinent may have formed, the continents drifting together as they have done repeatedly throughout Earth's history. The last supercontinent, Pangaea, existed about 300 million years ago. Before that, there were others, Rodinia, Columbia, Kenneland, stretching back billions of years. The assembly and breakup of supercontinents is one of the great cycles of Earth's geology, driven by convection currents in the mantle. The formation of a supercontinent has profound effects on climate. A large landmass concentrated near the equator absorbs more solar energy than ocean at the same latitude, because land has a lower heat capacity than water. The interior of a supercontinent tends to be extremely dry and hot, far from the moderating influence of the ocean. Monsoon circulation becomes extreme. The distribution of rainfall changes dramatically. At 2% brighter, the sun's extra energy is interacting with whatever continental configuration exists. The global average temperature might be 2 to 4 degrees higher than today, depending on the details of the geography and the response of the climate system. This is significant, comparable to the warming that occurred during some of the warmest periods in Earth's geological past, like the Eocene thermal maximum about 50 million years ago, when there was no ice at either pole and palm trees grew in the Arctic. But the Earth has been this warm before. Life survived, it adapted, it diversified. The warming at this stage is well within the range that the biosphere has experienced and endured. The sun's brightening is a problem, but not yet a crisis. 300 million years from now, the sun is about 3% brighter. This is where the first serious warning signs begin to appear, not for life in general, but for a specific and critical process that most of the biosphere depends on. That process is C3 photosynthesis. Photosynthesis, the process by which plants and algae convert carbon dioxide and water into glucose and oxygen using sunlight, comes in several varieties. The most common is C3 photosynthesis, used by the vast majority of plant species, including most trees, shrubs, and cool-season grasses. C3 photosynthesis has a problem. It becomes less efficient as temperatures rise and carbon dioxide levels fall. Here is the connection. As the sun brightens and the Earth warms, the rate of chemical weathering increases. Chemical weathering is the process by which rain, slightly acidified by dissolved carbon dioxide, reacts with silicate rocks on the surface, breaking them down and locking the carbon into carbonate minerals that are eventually carried to the ocean and deposited as sediment. This is part of the long-term carbon cycle, the geological thermostat that has kept Earth's climate relatively stable over billions of years. When the planet warms, weathering speeds up, drawing down more carbon dioxide from the atmosphere. When the planet cools, Weathering slows, allowing carbon dioxide to build up. This thermostat has worked remarkably well for most of Earth's history. But it has a limit. As the sun brightens, the thermostat compensates by drawing down more and more carbon dioxide. The atmospheric concentration of CO2 drops, and at some point it drops low enough that C3 photosynthesis can no longer function efficiently. The threshold is about 150 parts per million of carbon dioxide. Below this level, C3 plants cannot photosynthesize fast enough to sustain themselves. They wilt, they die. And since C3 plants make up the vast majority of Earth's vegetation, including most forests, the consequences would be catastrophic for the biosphere. Current estimates suggest that atmospheric CO2 could fall below the C3 photosynthesis threshold in about 500 to 600 million years. But some models place it earlier, depending on assumptions about weathering rates, volcanic outgassing, and biological adaptation. By 300 million years from now, CO2 levels may already be declining significantly, and the first stresses on C3 vegetation may be becoming apparent. Let's pause here for a moment. Take a slow breath. Let the scale of this settle. We are talking about a process, the decline of carbon dioxide in the atmosphere, that is driven not by anything humans are doing, but by the fundamental physics of a star getting brighter. The sun's increasing luminosity is, over geological time, slowly suffocating the plants that produce the oxygen we breathe. Not quickly, not dramatically, but steadily, inevitably, as the geological thermostat does its job too well, drawing down CO2 to compensate for the extra heat until there isn't enough CO2 left for the plants to survive. This is confirmed science. The chemical weathering feedback is well understood. The sensitivity of C3 photosynthesis to CO2 levels is well documented. The projection that CO2 will eventually fall below the threshold for C3 photosynthesis is accepted by the scientific community. The only uncertainty is the exact timing, 500 million years from now. The sun is about 5% brighter. This is where the timeline becomes truly consequential. At this point, atmospheric carbon dioxide has likely fallen to levels that make C3 photosynthesis impossible, or nearly so. The great forests of the Earth are gone. The grasslands are gone. The flowering plants that dominate today's landscapes are gone, at least in their current forms. What remains are C4 plants and CAM plants, species that use alternative photosynthetic pathways that are more efficient at low CO2 concentrations. C4 photosynthesis is used by some tropical grasses, corn, sugarcane, and certain other plants. CAM photosynthesis is used by cacti, succulents, and some other drought-adapted species. These plants can survive at lower CO2 levels than C3 plants, down to perhaps 50 to 10 parts per million. So the landscape of the Earth 500 million years from now might be dominated by C4 grasslands and CAM-adapted vegetation, a world very different from the one we know, but still green, still alive, still producing oxygen. But the respite is temporary. The sun continues to brighten. The thermostat continues to draw down CO2, and eventually, even C4 and CAM photosynthesis will be pushed to their limits. The loss of C3 photosynthesis will have cascading effects throughout the biosphere. Most of the world's ecosystems are built on C3 plants. Forests, which are overwhelmingly C3, are the habitat of countless animal species. The insects that pollinate C3 plants, the herbivores that eat them, the predators that eat the herbivores, All are part of food webs anchored to C3 vegetation. When C3 plants disappear, those food webs collapse. Animals that depend on C3 plants will go extinct unless they can adapt to C4-based ecosystems. Some will, many won't. The diversity of terrestrial life will decline sharply. The great complexity of Earth's biosphere, the result of hundreds of millions of years of evolution, will begin to unravel. In the oceans, the effects may be delayed. Marine photosynthesis depends on dissolved CO2 in seawater, and the ocean has enormous capacity to buffer changes in carbon chemistry. Phytoplankton, the microscopic algae that produce about half of Earth's oxygen and form the base of the marine food web, may survive longer than terrestrial plants. But they too will eventually be affected by the declining CO2 and the rising temperatures. 600 million years from now, the Sun is about 6% brighter. Atmospheric CO2 may have fallen below the threshold for virtually all photosynthesis. If this happens, the production of oxygen ceases. Not immediately. Oxygen is a relatively stable gas and would persist in the atmosphere for millions of years even without new production. But the writing is on the wall. Without photosynthesis, the oxygen will slowly be consumed by oxidation reactions, the rusting of iron, the decomposition of organic matter. The slow chemistry of weathering over tens of millions of years, oxygen levels will decline. The loss of oxygen does not mean the end of all life. Life existed on Earth for more than 2 billion years before oxygen became abundant in the atmosphere. The earliest life forms were anaerobic, thriving in oxygen-free environments. There are still vast communities of anaerobic microorganisms living in the deep subsurface, in ocean sediments, in hot springs, in environments where oxygen never reaches. These organisms could persist long after the oxygen breathers are gone. But the world of complex, multicellular oxygen-breathing life, the world of animals and plants and fungi that we know, would be over. The great experiment of complex life on Earth, which began perhaps 600 million years ago with the Cambrian explosion, would come to an end not with a bang, but with a slow, quiet suffocation. Let's take a breath. Let this moment settle. Close your eyes if they aren't already closed. Imagine the Earth 600 million years from now. The continents have been rearranged by plate tectonics, perhaps assembled into a new supercontinent, perhaps scattered again. The mountains are different, the coastlines are different, but the biggest change is the silence. No birds singing. No insects humming, no rustle of leaves in the wind because there are no leaves. The land is bare rock and soil, perhaps with a thin crust of microbial life, the hardy survivors of a world that no longer supports anything larger or more complex. The oceans are warmer, perhaps by 10 or 15 degrees, and their chemistry is changing, becoming more acidic or more alkaline depending on the details of the carbon cycle. The sky is still blue because the atmosphere still scatters light. But the air is thinner, drier, with less oxygen and less CO2. And the sun, the familiar yellow sun that has lit every day of every life that has ever existed, is noticeably brighter, hotter, more insistent. 700 million years from now, the sun is about 7% brighter. Global average temperatures have risen significantly, perhaps to 30 or 40 degrees Celsius, depending on the state of the atmosphere and the configuration of the continents. The oceans are still present, but they are beginning to lose water, not through boiling, not yet. Through a more subtle process called the moist greenhouse effect. Here's how it works. As temperatures rise, more water evaporates from the oceans into the atmosphere. Water vapor rises to the upper atmosphere, where it is broken apart by ultraviolet radiation from the sun into hydrogen and oxygen. The hydrogen, being the lightest element, escapes into space. This process, called hydrogen escape, is slow but steady, and over hundreds of millions of years, it removes water from the Earth permanently. The moist greenhouse effect is a critical threshold in planetary science. It represents the point at which a planet begins to lose its water irreversibly. Venus probably crossed this threshold early in its history, losing whatever water it once had through exactly this mechanism. Earth is heading toward the same fate, driven not by a runaway greenhouse effect from CO2, but by the slow, steady increase in solar luminosity. The moist greenhouse threshold is estimated to occur when the solar flux reaching the Earth increases by about 10 to 20% above current levels. That puts it somewhere between 700 million and 1 billion years from now, depending on the details of the atmospheric model. Some models place it earlier, some later. The uncertainty arises from the complexity of the climate system, the role of clouds, the interaction between water vapor and other greenhouse gases, and the response of the surface and oceans, but the direction is not uncertain, only the timing. The Earth will enter the moist greenhouse. The oceans will begin to evaporate, and the water that escapes into space will never come back. 800 million years from now, the sun is about 8% brighter. The moist greenhouse effect is well underway. The upper atmosphere is loaded with water vapor, and hydrogen is escaping to space at an accelerating rate. The oceans are shrinking, slowly but measurably. Sea levels are dropping, not because water is freezing into ice, but because water is literally leaving the planet. At the surface, temperatures continue to climb. The remaining oceans are warm, perhaps 50 degrees Celsius or more in the tropics. Complex marine life, if any survives, is restricted to the cooler polar regions or the deepest ocean layers. The shallow tropical seas that were once cradles of biodiversity are now too hot for most organisms. On land, the situation is even more severe. Without plants, there is no shade, no transpiration, no biological cooling. The bare rock absorbs solar energy and radiates it back as heat. Daytime temperatures in the tropics may exceed 60 or 70 degrees Celsius, well above the thermal tolerance of most known organisms. Even the hardiest extremophile bacteria struggle above about 120 degrees Celsius, but surface temperatures are not yet that extreme. Life persists, but it is retreating to the poles, to the deep ocean, to the subsurface, to the last refuges where temperatures are still bearable. Let's pause here, let's breathe. This is a hard part of the story, not because of the numbers, but because of what they mean. The Earth that we know, the Earth of forests and oceans and teeming life, is dying, slowly over hundreds of millions of years, but dying nonetheless, killed not by an asteroid or a supervolcano or a gamma-ray burst, but by the gentle, patient, unstoppable brightening of its own star. The same sun that made life possible is now making life impossible. The same energy that warmed the primordial oceans and powered the evolution of every living thing is now incrementally cooking the planet. There is a tragic irony in this. The sun doesn't know what it's doing. It's not malicious. It's not even aware. It is simply a ball of hydrogen and helium, doing what the laws of physics require it to do, fusing atoms in its core and radiating the energy outward. The brightening is an inevitable consequence of its internal chemistry, as predictable and as impersonal as gravity. And yet, the consequences for the third planet from the Sun are profound and final. 1 billion years from now, the Sun is about 10% brighter. This is a major threshold. At this luminosity, most models predict that the Earth will enter or be well into the moist greenhouse state. The oceans are significantly depleted. Some models suggest that a substantial fraction of Earth's water, perhaps half, has been lost to space by this point. Others suggest the loss is slower and significant oceans remain. The uncertainty depends on cloud feedbacks, atmospheric chemistry, and other factors that are difficult to model precisely over such long timescales. But the trend is clear. The Earth is drying out. The great oceans that have covered the planet for more than 4 billion years are shrinking. The water cycle, the engine of weather and climate, is weakening. Rainfall is declining as there is less water to evaporate. The continents already stripped of vegetation are becoming vast, dry, dusty expanses, baked by a sun that is noticeably brighter and hotter than the one we know. If any complex life survives at this point, it is likely restricted to the deep ocean, where temperatures are moderated by the thermal inertia of the remaining water, or to the deep subsurface, where organisms can shelter from the heat and find water in underground aquifers. The surface is hostile. The era of surface life, the era of creatures that walk and fly and swim under an open sky, is drawing to a close. 1 billion years from now is, in many respects, the effective end of the biosphere as we understand it. Not the end of all life. Microbial life in the subsurface may persist for much longer, but the end of the rich, complex, diverse biosphere that has made Earth unique in the known universe. The forests, the coral reefs, the grasslands, the wetlands, the teeming ecosystems that have evolved over billions of years, all gone. Victims of a star that is simply following the laws of physics. Let's sit with that for a moment. 1 billion years. It sounds like a long time, and it is. It is roughly the same amount of time that has elapsed since the first multicellular animals appeared on Earth. In 1 billion years from now, the Earth will have traveled one full orbit around the center of the Milky Way, a journey of about 225 million years per orbit, so about 4 more galactic years. 1 billion years is enough time for evolution to produce entirely new kingdoms of life, for continents to assemble and break apart multiple times, for mountain ranges to rise and erode to nothing. But it is not enough time to outrun the Sun. 1 billion years is the approximate expiration date for the complex biosphere. After that, the Earth is a simpler, harsher, lonelier place, and the Sun keeps brightening. 1.5 billion years from now, the Sun is about 15% brighter. The oceans are in serious decline. Some models suggest that by this point, the oceans are largely gone, evaporated into the atmosphere and lost to space. The Earth's surface may resemble Venus, a hot, dry, rocky world with a thick, steamy atmosphere, though the details depend heavily on how much water remains and how the atmosphere evolves. Without oceans, plate tectonics may slow or stop entirely. This is a critical point. Plate tectonics requires water. Water in the mantle lowers the melting point of rock, enabling the convection currents that drive tectonic plates. Water in subduction zones lubricates the descent of oceanic crust into the mantle. Without water, the mantle becomes stiffer, the plates become locked, and the great engine of geological recycling grinds to a halt. The consequences of losing plate tectonics are profound. Without subduction, there is no volcanic recycling of carbon from the mantle to the atmosphere. Without volcanism, the long-term carbon cycle shuts down. Without the carbon cycle, there is no geological thermostat to regulate climate. The Earth becomes geologically dead, a static world of ancient, unrecycled rock, slowly cooking under an ever-brightening sun. Mars may have lost its plate tectonics billions of years ago, when it cooled enough for its mantle to stiffen. Mars is now a geologically dead world, with no volcanic activity, no tectonic recycling, no magnetic field. Earth may be heading for the same fate, not because it is cooling, but because it is losing the water that keeps its geology alive. 2 billion years from now, the Sun is about 20% brighter. If the oceans are gone, the surface of the Earth is now baked by a Sun that pours 20% more energy onto every square meter than it does today. Surface temperatures may exceed 100 degrees Celsius in the tropics, well above the boiling point of water at sea level pressure. But without oceans, there is no sea level. The atmosphere itself may be changing, losing its oxygen as the last reserves are consumed by oxidation, gaining carbon dioxide from volcanic outgassing if any volcanism remains, or losing atmosphere entirely to the solar wind if the magnetic field has weakened. Life, if it persists at all, is deep underground. Microbial communities in the subsurface, living in pore spaces in rock, feeding on chemical energy from mineral reactions, shielded from the hellish surface by kilometers of stone. These organisms would be the last descendants of the great tree of life that began nearly 4 billion years ago. And they would be living on borrowed time because the heat is penetrating deeper and the subsurface temperatures are rising. Let's take a breath. Let the room around you be still. We are deep into the future now, 2 billion years, twice the age of the first animals, a span of time so vast that it encompasses most of the history of complex life on Earth. And in this future, that complexity is gone. The Earth is a dying world, baking under a brightening sun, stripped of its water, losing its atmosphere, its geology shutting down, and the Sun is only halfway through its main sequence life. It still has another 3 billion years of hydrogen fusion ahead of it. And it's going to keep getting brighter. 2.5 billion years from now. The Sun is about 25% brighter. The Earth's surface is extremely hot. If any atmosphere remains, it is thin and dry, perhaps mostly nitrogen and carbon dioxide with traces of noble gases. The surface is bare rock, cracked and weathered, with no soil because there are no biological processes to create soil and no water to transport sediment. The landscape is utterly lifeless, a world of stone and dust under a relentless blazing sun. The magnetic field may have weakened significantly by this point. The Earth's magnetic field is generated by convection currents in the liquid outer core, driven by the planet's internal heat. But the Earth has been slowly cooling for billions of years, and the inner core has been growing as the outer core solidifies. Eventually, the outer core will solidify completely, and the magnetic field will shut down. Current estimates suggest this will happen in about 1.5 to 2.5 billion years, though the uncertainty is large. Without a magnetic field, the Earth is exposed to the full force of the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. The solar wind gradually strips away the atmosphere, molecule by molecule, in a process called atmospheric sputtering. Mars, which lost its magnetic field early in its history, has been losing its atmosphere to the solar wind for billions of years, and its current atmosphere is less than 1% the density of Earth's. The same process will eventually strip Earth's atmosphere, leaving the surface fully exposed to solar radiation and the vacuum of space. 3 billion years from now, the Sun is about 30% brighter. The Earth may have lost most or all of its atmosphere by this point, depending on how quickly the magnetic field weakened and how aggressive the solar wind has been. Without an atmosphere, the surface is directly exposed to solar radiation, including ultraviolet and X-ray wavelengths that are currently absorbed by the atmosphere. The surface temperature swings wildly between day and night, hundreds of degrees hot on the sunlit side, desperately cold on the dark side, with no atmosphere to moderate the extremes. But this assumes the Earth is still rotating at roughly its current rate. Over 3 billion years, the Moon's tidal braking will have slowed the Earth's rotation significantly. The day will be longer, perhaps 30 or 40 hours, and the temperature extremes between day and night will be even more severe, with longer exposure to the blazing sun on one side and longer periods of radiative cooling on the other. The Moon itself will be farther away. Currently about 384,000 kilometers from Earth, the Moon is receding at about 3.8 centimeters per year due to the transfer of rotational energy from Earth to the Moon's orbit. Over 3 billion years, that adds up to about 114,000 kilometers, putting the Moon at roughly 500,000 kilometers. The Moon will appear smaller in the sky. Total solar eclipses will no longer be possible, because the Moon's apparent size will be too small to cover the Sun. Not that there will be anyone to watch. Let's pause again. Breathe slowly. Let the numbers fade and just feel the image. The Earth, 3 billion years from now, a barren, airless, rotating rock, circling a sun that is 30% brighter than today, no oceans, no atmosphere, no life on the surface, no magnetic field, just stone and dust and silence, baking under a white-hot sun in the emptiness of space. And deep, deep underground, perhaps, the last microbes, the final survivors of 4 billion years of evolution, clinging to existence in the slowly warming rock, or perhaps not. Perhaps even they are gone by now, the subsurface temperatures finally exceeding the limits of even the most extreme thermophiles. It is a lonely image, but the story is not over. The sun still has fuel to burn, and what comes next is even more dramatic, 3.5 billion years from now. The sun is about 35% brighter. The interior of the sun is undergoing subtle but important changes. The helium ash in the core is building up, creating an inert helium core that cannot fuse at the temperatures and pressures currently available. The hydrogen fusion is now happening in a shell surrounding this helium core, burning outward like a ring of fire. The energy output continues to increase, slowly but inexorably. The Earth is, by human standards, already dead. But it still exists as a physical body, still orbiting the sun, still rotating on its axis, still subject to the laws of gravity and orbital mechanics. Its surface may be slowly ablated by the solar wind, losing mass molecule by molecule, but the rate is slow enough that the planet itself will persist as a rocky body for billions of years to come. 4 billion years from now, the sun is about 40% brighter. And something remarkable is about to happen in the wider cosmos, though it has nothing to do with the sun. The Andromeda Galaxy, currently about 2.5 million light-years away, is on a collision course with the Milky Way. The two galaxies are approaching each other at about 110 kilometers per second, and in roughly 4 to 5 billion years, they will collide. The merger will transform both galaxies. Tidal forces will distort their shapes, pulling out long streamers of stars, triggering bursts of new star formation, and eventually merging the two spirals into a single larger elliptical galaxy. But the collision will have virtually no effect on the Sun or the Earth. The distances between individual stars in a galaxy are so vast that stellar collisions during a galactic merger are extraordinarily rare. The Sun will sail through the merger essentially unscathed, perhaps shifted to a different orbit within the new galaxy, but otherwise unaffected. It's a curious thought. The Earth, by this point, long dead, lifeless, stripped of its oceans and atmosphere, will witness one of the most dramatic events in the local cosmos, the collision of two galaxies, and be completely unaffected by it. The scales are just too different. The distance between stars is measured in light years. The distance from the Sun to the Earth is measured in light minutes. The galaxy merger is a spectacle for hypothetical observers, but it changes nothing about the Sun's evolution or the Earth's fate 4.5 billion years from now. The Sun is about 45% brighter. The helium core has been growing steadily, and the hydrogen-burning shell is moving outward. The Sun's structure is beginning to change in ways that will accelerate in the coming hundreds of millions of years. 5 billion years from now. This is the approximate point at which the Sun exhausts the hydrogen in its core. The core is now almost pure helium, dense and hot, but not hot enough to fuse helium into heavier elements. Without nuclear fusion to support it, the core contracts under its own gravity. As it contracts, it heats up. And the hydrogen-burning shell, now sitting on top of a hotter, denser core, burns more fiercely. The energy output increases dramatically. The Sun begins to leave the main sequence. It is entering the subgiant phase, the beginning of its transition from a stable, hydrogen-burning star to a red giant. This is the beginning of the end for the Sun and for the Earth. The subgiant phase lasts about 1 billion years. During this phase, the Sun gradually swells and brightens. Its surface temperature actually decreases slightly because the energy is being spread over a larger surface area. The Sun becomes larger and redder, shifting from its current yellowish-white color toward orange and eventually toward red. Let's breathe here. We are approaching the most dramatic chapter of this story. The Sun is about to become a giant, and the Earth, already dead and lifeless, is about to be transformed once more, this time physically, as the expanding Sun engulfs its orbit 5.5 billion years from now. The Sun has entered the red giant branch. This is where the transformation becomes rapid by astronomical standards. The hydrogen-burning shell continues to intensify, and the extra energy causes the Sun's outer layers to expand enormously. The Sun swells to many times its current size, its surface pushing outward past the orbit of Mercury, past the orbit of Venus. The expansion is not gradual and steady, it comes in pulses and surges, driven by instabilities in the hydrogen-burning shell. The Sun's luminosity increases dramatically, to perhaps 1,000 times or more its current value. The Earth, even though it has been lifeless for billions of years, is now being bathed in radiation intense enough to melt rock. The surface of the Earth, whatever remains of it, is being heated to temperatures of 1,000 degrees Celsius or more. The rock is softening, beginning to glow with a dull red heat. If any iron or nickel remains on the surface, it is melting. If any lighter minerals remain, they are vaporizing. The Earth is being roasted by its own star. 6 billion years from now, the Sun is a full red giant. Its radius has expanded to about 1 astronomical unit, the current distance from the Sun to the Earth, roughly 150 million kilometers. The Sun fills the entire sky of the inner solar system, a vast red glowing wall of hydrogen and helium. But here is a subtlety that is often overlooked. As the Sun expands and loses mass through its intensifying solar wind, the orbits of the planets expand. The Sun on the red giant branch is losing mass at a rate much higher than it does now, shedding material from its outer layers into space. As the Sun loses mass, its gravitational pull weakens and the planets spiral outward to larger orbits. The Earth's orbit may expand by 10 to 50%, depending on how much mass the Sun loses, and when this orbital expansion might save the Earth from being engulfed, maybe the calculations are close. Some models predict that the Earth's orbit will expand fast enough to stay ahead of the expanding Sun. Others predict that the Sun will expand faster than the orbit retreats and the Earth will be engulfed. The outcome depends on details that are difficult to calculate precisely, including the rate of mass loss, the timing of thermal pulses, and the effects of tidal interactions between the expanding Sun and the nearby planets. In 2008, a detailed study by astronomers Klaus-Peter Schroeder and Robert Conan Smith concluded that the Earth will most likely be engulfed by the Sun during its red giant phase. Their models showed that tidal interactions between the expanding Sun and the Earth will actually drag the Earth inward, counteracting the outward expansion of the orbit due to mass loss. The Earth spirals into the Sun's outer envelope and is destroyed. Other researchers have reached different conclusions, and the question is not fully settled, but the most likely outcome based on current models is that the Earth will be engulfed. Not immediately, not in a single dramatic moment. But gradually, as the Sun's outer layers expand to encompass the Earth's orbit, and the planet finds itself moving through the tenuous but real gas of the Sun's extended atmosphere, drag forces slow the Earth's orbital velocity, causing it to spiral inward. And eventually, the Earth falls into the Sun and is vaporized. Let's sit with that image. The Earth vaporized. The planet that was home to everything we've ever known, every civilization, every species, every ocean and mountain and sunset, reduced to a cloud of atoms dispersing into the outer layers of a dying star. The iron from its core, the silicon from its mantle, the oxygen that once filled its atmosphere, the carbon that once formed the backbone of every living molecule, all of it absorbed into the Sun's bloated envelope, mixed with the hydrogen and helium that have been fusing for 11 billion years. It is total, it is final. The Earth is gone, but the Sun's story continues. After spending perhaps 1 billion years on the red giant branch, the Sun's helium core becomes hot enough, about 100 million degrees Celsius, to ignite helium fusion. In a dramatic event called the helium flash, the helium core ignites nearly simultaneously throughout, releasing an enormous burst of energy, but this energy is absorbed by the core itself and does not reach the surface. The Sun adjusts its structure, settles onto what is called the horizontal branch, and begins a period of more stable helium burning, fusing helium into carbon and oxygen. This phase lasts about 100 million years. During this time, the Sun is smaller than its red giant maximum, perhaps a few tens of times larger than its current size and somewhat less luminous. It is a brief respite, a momentary settling before the final act. After the helium in the core is exhausted, the Sun enters the asymptotic giant branch, a second red giant phase that is even more extreme than the first. The Sun swells again to sizes comparable to, or even larger than its first red giant maximum. It becomes unstable, pulsating and shedding mass in powerful stellar winds. The outer layers are expelled into space in a series of thermal pulses, creating a beautiful expanding shell of gas and dust called a planetary nebula. The name planetary nebula is a historical misnomer. These objects have nothing to do with planets. They were named by early astronomers who observed them through small telescopes and thought they resembled the disks of planets. In reality, they are the shed outer layers of dying stars, illuminated by the intense ultraviolet radiation from the exposed stellar core. And that core, now exposed, is the final remnant of the Sun. It is called a white dwarf. A white dwarf is an extraordinarily dense object, about the mass of the Sun compressed into a sphere about the size of the Earth. A teaspoon of white dwarf material would weigh about 5 tons. White dwarfs are not powered by nuclear fusion. They are simply cooling, slowly radiating away the heat stored in their interiors, fading from white to yellow to orange to red over billions of years. The Sun's white dwarf will have a surface temperature of about 100,000 degrees Celsius when it is first exposed, making it intensely bright in ultraviolet light, but it will cool rapidly at first, then more slowly, dimming over billions of years. After about 1 billion years, it will have cooled to a surface temperature of perhaps 10,000 degrees, a faint, warm, white-hot ember. After 10 billion years, it will be even cooler, a dim, reddish point of light. After 100 billion years, it will be barely visible, a dark, dense cinder, still massive, but producing almost no light. The planetary nebula, the shed outer layers of the Sun, will disperse into interstellar space over tens of thousands of years, mixing with the gas and dust between the stars, enriching the interstellar medium with the carbon, nitrogen, oxygen, and other elements that the Sun produced during its life. These elements will eventually be incorporated into new clouds of gas and dust, new generations of stars and planets, new worlds. The atoms that once made up the Sun and the Earth, and everything that ever lived on the Earth, will be recycled, scattered across the galaxy, used again and again in the endless cycle of stellar birth and death. Let's take a long, slow breath here. The Sun is dead. The Earth is gone. The solar system, as a dynamic living system, is over. What remains is a white dwarf, slowly cooling in the darkness, orbited perhaps by the outer planets Jupiter, Saturn, Uranus, and Neptune if they survive the red giant phase, their orbits expanded by the Sun's mass loss but still gravitationally bound. They are dark now, receiving no warmth from the fading ember at the center of the system. Their atmospheres are frozen. Their moons are dark. The solar system is a cold, quiet graveyard, lit only by the faint glow of the dying white dwarf and the distant light of other stars. But the white dwarf will persist for an extraordinarily long time. The cooling time for a white dwarf is measured in trillions of years. Long after the last main sequence stars in the universe have burned out, long after the galaxies have dissolved and the cosmic background radiation has faded to near absolute zero, the white dwarfs will still be there, slowly, patiently cooling the last embers of the stellar era, the faintest. Memories of the Age of Light. Let's step back now from the timeline and reflect on what we've walked through. The Sun was born about 4.6 billion years ago from a cloud of gas and dust. It ignited its nuclear furnace, and the Earth formed from the leftover material. For the first few 100 million years, the Earth was a hellish, molten world bombarded by asteroids, devoid of life. Then, somewhere between 3.5 and 4 billion years ago, life appeared. Simple, single-celled organisms, the ancestors of everything that has ever lived. For the next 2 billion years, life remained simple, single-celled, microbial, but it was busy. Cyanobacteria evolved photosynthesis and began pumping oxygen into the atmosphere, transforming the planet's chemistry. About 2.4 billion years ago, oxygen accumulated to significant levels in the atmosphere, an event called the Great Oxidation Event, which was both a catastrophe for the anaerobic organisms that had dominated until then, and an opportunity for the oxygen-breathing organisms that would eventually include us. About 600 million years ago, complex multicellular life exploded in diversity during the Cambrian period. Animals appeared. Plants colonized the land about 470 million years ago, insects about 400 million years ago, reptiles about 300 million years ago. Dinosaurs about 230 million years ago, mammals about 200 million years ago, flowering plants about 130 million years ago. The dinosaurs went extinct 66 million years ago, allowing mammals to diversify and eventually produce primates, hominids, and, about 300,000 years ago, Homo sapiens. All of this, the entire history of life on Earth, from the first microbe to this quiet moment, has taken place in roughly the first half of the Sun's main sequence life. The Sun was bright enough to warm the Earth, but not so bright that it overheated. The conditions were just right for about 4 billion years, but the window is closing. The Sun's brightening is now working against life, not for it. The same energy that made life possible is becoming the force that will end it. And the timeline we've walked through tonight, from the first stresses on C3 photosynthesis in a few 100 million years to the final engulfment of the Earth in 6 billion years, is the story of that closing window. It is, in its own way, a beautiful story. Not because the ending is happy, but because the story itself is so improbable. The fact that a ball of hydrogen and helium, ignited by gravity, could create a system of planets and moons, could warm one of those planets just enough for chemistry to become biology, for biology to become consciousness, for consciousness to look up at the star that made it and understand with mathematical precision how that star will eventually destroy everything it created. That is extraordinary. That is perhaps the most remarkable thing in the entire observable universe. The Sun doesn't know that we're here. It doesn't know that it created us. It doesn't know that it will destroy us. It is simply a star, following the laws of physics, converting hydrogen to helium and radiating the energy into space. It has done this for 4.6 billion years. It will do it for another 5 billion. And then it will swell, shed its outer layers, and fade to a white dwarf, a cooling ember in the darkness, carrying the atoms of the Earth in its fading glow. Let your mind settle now. Let the numbers and the timeline soften into a feeling. You don't need to hold on to the details. They'll be there in the morning. The sun will be there in the morning, rising as it has every morning since the earth was born, warming your skin, lighting the sky, making possible everything that lives and breathes and thinks on this small, fragile, beautiful planet. And for now, for this brief moment in cosmic time, the sun is just right. Not too bright, not too dim. The oceans are full, the air is breathable, the forests are green, the birds are singing somewhere in the world right now. Even as you listen to this, life is thriving. And it will continue to thrive in one form or another for hundreds of millions of years to come. The ending is far away, so far away that it is almost meaningless on a human timescale. But knowing that it's coming, knowing that the sun's brightening is a countdown that cannot be stopped, gives this present moment a quality that it might not otherwise have. A preciousness, a weight. This moment, this breath, this heartbeat, this quiet, comfortable darkness around you. All of it is possible because a star is burning at exactly the right brightness, at exactly the right distance, at exactly the right moment in its life. And it won't always be this way. The window will close, the sun will brighten, the oceans will evaporate, the air will thin. The life will retreat, simplify, and eventually vanish. And the earth will become another silent, barren world, circling a star that is too bright, too hot, too old to sustain the miracle it once created. But that's billions of years away. Billions, not thousands, not millions, billions. The number is so large that it dwarfs everything in human experience. The entirety of recorded human history, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the space age, all of it fits into about 5,000 years. 5,000 years out of 5 billion. That's 1/1,000,000th of the time remaining. 1/1,000,000th, the sun has barely begun its work on the earth, and the earth has barely begun its journey through the sun's life. You are here. At the very beginning of the end, which is so far from the end itself that calling it the beginning is almost a joke. You are in the sweet spot, the golden age. The era when a planet orbits its star at just the right distance, with just the right atmosphere, with just the right chemistry, and complex life is not only possible but abundant. This era will not last forever. But it has lasted for hundreds of millions of years already, and it will last for hundreds of millions more. That's time enough for evolution to produce wonders beyond anything we can imagine. Time enough for civilizations to rise and fall, for intelligence to emerge and re-emerge, for life to find new forms and new strategies, adapting to the slowly changing conditions until the conditions become, finally, too extreme. And then, after the last organism on the last refuge on the dying earth exhales its last breath, the story of life on this planet will be over, but the atoms will remain. The carbon and oxygen and nitrogen and iron that made up every living thing will persist, scattered through the sun's outer layers, dispersed into the interstellar medium, eventually incorporated into new stars, new planets, new worlds. The matter that was you, that was every person who ever lived, that was every tree and fish and bird and bacterium that ever existed on this planet, will go on, not as life, not as consciousness, but as matter, as atoms. As the raw material of the cosmos, recycled endlessly, used and reused in the great furnace of stellar evolution. There is something comforting in that. Not comfortable, not reassuring in the human sense, but comforting in a deeper, quieter way. The universe does not waste, it recycles. The death of one star is the birth of another. The destruction of one world is the creation of the next. The atoms in your body were forged in stars that died before the sun was born, and the atoms in your body will be part of stars and planets that haven't been born yet. The cycle continues. The story goes on, even after our chapter ends. Let the thought drift now. Let it become background. The sun is in the sky, or it will be in a few hours, rising in the east as it always does, as it has done every morning for 4.5 billion mornings, and as it will do for 5 billion more. The sunrise is the most familiar, most constant, most reliable thing in human experience. And behind its familiarity, behind its warmth and beauty, is a nuclear furnace that is slowly, imperceptibly getting brighter, converting hydrogen to helium, building up ash in its core, inching toward a future that will transform the solar system, but not tonight. Tonight, the sun is below the horizon, or it's shining on the other side of the world, lighting some other patch of ocean or forest or city. And you are here in the dark, listening to this voice, thinking about timescales so vast that they make human life seem like the blink of an eye, and in a way, it is. In the life of a star, a human life is a flicker, a civilization is a spark. The entire history of life on Earth is a single chapter in the story of the sun. But it is a chapter worth reading, a chapter full of beauty and complexity and improbable wonders, a chapter that includes you, here, now, breathing, thinking, existing. In the middle of the sun's life, in the middle of the Earth's life, in the golden age of the solar system, a brief, bright, beautiful moment in a story that stretches across billions of years. Think about the sun as it is right now. A sphere of hydrogen and helium, 1.4 million kilometers across, 150 million kilometers away, converting 600 million tons of hydrogen to helium every second, radiating 3.83 times 10 to the 26 watts into space. A power output so enormous that even at a distance of 150 million kilometers, it lights our days, drives our weather, grows our food, and warms our skin. All of that from a ball of gas that is simply falling inward under its own gravity, hot enough at the center to force atoms together. The sun has been doing this for longer than there have been eyes to see it, longer than there have been creatures to feel its warmth, longer than there has been land to walk on or water to swim in. The sun was here first. It created the stage on which all of Earth's drama has played out. And it will be here after the curtain falls, continuing to burn, continuing to brighten, continuing to follow the path laid out by the laws of physics, indifferent to the life it once sustained. But we are not indifferent. We are the opposite of indifferent. We look up at the sun and see not just a star, but the source of everything, the engine of our existence, the light that makes life possible. And knowing that it will one day make life impossible, knowing that the same fire that warms us will eventually consume us, gives us a perspective that no other species on this planet has ever had. We can see the end, we can calculate it, we can understand it. And we can choose what to do with the time we have. 500 million years of complex life remaining. Maybe more, maybe less, depending on the details. But order of magnitude, 500 million years, that's an ocean of time. Enough for evolution to produce new forms of life we can't begin to imagine. Enough for intelligence to arise again if it were to vanish tomorrow. enough for civilizations to spread across the solar system, perhaps even to other stars, carrying the flame of consciousness beyond the reach of the brightening sun. That's the other side of this story, the hopeful side. The fact that we know the sun's timeline means we can, in principle, prepare for it, not as individuals, not even as a civilization in its current form, but as a species, as a lineage. As a tradition of intelligence and curiosity and determination that might, over hundreds of millions of years, find ways to outlast the sun, move to Mars, move to the outer solar system, move to other stars. Or find some way to engineer the sun itself, to extend its main sequence life, to manage its energy output, to postpone the red giant phase. These are ideas that are currently in the realm of science fiction. But 100 million years ago, the idea of multicellular life would have been science fiction too. The future is long, and the potential of intelligence, given enough time, is impossible to estimate. But those are thoughts for another night. Tonight, we rest. We let the sun story settle into us like warmth, like the warmth of the sun itself, distant and reliable and comforting. The sun will rise in the morning, it will set in the evening, it will do this tomorrow and the day after that, for as long as there is an earth to shine upon. And somewhere deep inside its core, hydrogen atoms are fusing into helium, and the clock is ticking. 1% brighter every 100 million years, a quiet, patient, unstoppable countdown. But the countdown has billions of years left to run. And right now, in this moment, the sun is exactly right. The earth is exactly right. And you are here, exactly right. Breathing and resting and existing in the warmth of a star that made you possible. The sun is the oldest thing in your daily experience. Older than the mountains. Older than the oceans. Older than the continents. Older than life itself. When you feel its light on your face, you're feeling the output of a nuclear furnace that has been burning since before the Earth existed. A furnace that will continue burning for longer than the Earth will exist. A furnace that is at this very moment, in the middle of its life, steadily burning, steadily brightening, steadily counting down to a future that is as certain as anything in science. But certainty, in this case, is not anxiety. It is perspective. It is the long view, the view from the scale of stellar lifetimes where human worries and human urgencies are set against a backdrop so vast that they become not insignificant, but differently significant, important in a different way. Important not because the universe cares about them, but because we care about them. And our caring is itself a remarkable thing, a thing the universe produced through billions of years of stellar evolution and planetary chemistry and biological complexity. Our caring is made of stardust. Our worry is made of hydrogen that was forged in the Big Bang. Our love is made of carbon that was cooked in the core of a star that died before the sun was born. We are the universe, looking at itself, worrying about itself, caring about itself, and the sun is the local chapter of that story. The star that made the planet, that made the life, that made the minds that can understand the star. A circle, a loop, a beautiful temporary luminous loop that will, in time, come undone. But not tonight. Tonight the loop holds. The sun is below the horizon, resting as much as a nuclear furnace can rest. The earth is turning, carrying you through the night toward another sunrise. And the stars are out, if you could see them, scattered across the sky like grains of light, each one a sun, each one with its own timeline, its own countdown, its own story of brightening and expansion and death. Some of those stars are younger than the Sun, still in the early stages of their main sequence lives, with billions of years of stable burning ahead. Some are older, nearing the end, swelling into giants, shedding their outer layers, fading into white dwarfs. Some have already died, their light still traveling through space, carrying the news of their death to observers who won't receive it for thousands or millions of years. The sky is a time machine. Every star you see is a snapshot from the past. And every star is at a different point in the same story that the Sun is telling. The story of hydrogen becoming helium, the story of gravity and fusion, the story of light and time, and the slow, patient aging of the cosmos. You are part of that story, a small part, a brief part, but a real part. The Sun made you, the Earth shaped you, and the billions of years that stretch ahead. The brightening and the warming and the evaporation and the expansion and the death, all of that is part of the story too. Your story, our story. The story of a star and its planet, and the life that flickered into existence between them, brief and bright and beautiful, a candle flame in the vastness of space. Let your eyes close. Let your breathing slow. The sun will rise in the morning. It always does. And when it does, it will be 100 millionth of 1% brighter than it was yesterday. You won't notice. Nobody will notice, but the clock is ticking, gently, patiently, relentlessly. 1% per 100 million years. A countdown measured not in seconds or minutes, but in eons. And in the warmth of that countdown, life thrives. You thrive. This moment thrives. And that is enough, more than enough. It is everything. The stars will still be there in the morning. Sleep well.